Let's start with something simple. Let's start with just how big is space, really? It's a strange question because our brains were never built to hold numbers like this. We evolved to understand the size of a cave, the distance to the next village, the height of a tree. We were not built to understand the size of the universe. And yet, here we are, trying anyway. So let's take it slowly. You know how far it is to the moon, more or less. It feels far, but it's not really. If you could drive a car straight up into the sky at highway speed, you'd reach the moon in about 160 days. Half a year of driving, and you'd arrive at our nearest neighbor in space. Now, the sun is much farther. If you kept driving at that same highway speed, it would take you 176 years to reach the sun. Multiple lifetimes. Just to get to the star at the center of our own solar system, the one whose light warms your skin on a summer day. But even the sun is close in the grand scheme of things. It's just next door. The next nearest star to us, a small reddish star called Proxima Centauri, is so far away that light itself, moving at the fastest speed anything can move, takes over 4 years to get there from here. 4 years. Not for a car, not for a rocket, for light. The fastest thing in the universe still needs 4 years to cross that gap. Let that sit for a moment. When you look up at a star, even one of the close ones, you are never seeing it as it is right now. You are seeing light that left it years ago, sometimes centuries ago, sometimes so long ago that the star itself might not even exist anymore. You could be looking at a ghost of light traveling toward you long after its source went dark. Every time you look up at night, your sun and its planets together are just one small system inside something much bigger. We live inside a galaxy called the Milky Way. Our galaxy contains, by most estimates, somewhere between 100 billion and 400 billion stars. Not planets. Stars, suns like ours, some bigger, some smaller, scattered across an enormous spinning disk of gas and dust and light. And our galaxy, as huge as that sounds, is just one galaxy. Scientists estimate there are somewhere around 2 trillion galaxies in the observable universe. 2 trillion. Each one containing billions of stars of their own. It's almost impossible to picture. If you tried to count every star and every galaxy in the observable universe, one per second, you would still be counting long after every human being currently alive has died, and their children, and their children's children. And here's the part that tends to be the most calming, oddly enough. All of that vastness, all of those trillions of galaxies, all of that light traveling for billions of years across empty space, none of it is going anywhere in a hurry. The universe is patient. It has been patient for over 13 billion years, and it will go on being patient long after we're gone. There's something soothing in that, if you let it be. You don't have to keep up with any of it. It's simply happening, slowly, all around you, all the time, whether you're awake to think about it or not. Let's slow down even more and talk about how it all started in the first place. Most cosmologists believe the universe began around 13.8 billion years ago in an event we call the Big Bang. It's a slightly misleading name because it wasn't really an explosion happening in space. It was the beginning of space itself. Before that moment, there was no before in the way we normally think about time. Space and time themselves began together. The universe was unbelievably hot and dense, smaller than an atom, yet containing everything that would eventually become everything. Then it began to expand. Not explode outward into some pre-existing empty room, but stretch, the way dough stretches when you pull it, carrying the raisins inside it farther apart from each other, even though none of the raisins are moving through the dough themselves. Space itself was the dough. Galaxies are the raisins. That expansion never stopped. It's still happening right now, while you lie there listening to this. The universe is getting bigger this very second, in every direction at once, silently, all around you. For a long time after the Big Bang, the universe was too hot for atoms to even form. Just a hot soup of particles, glowing and dense. It took around 380,000 years for things to cool down enough for the first true atoms to form, mostly hydrogen, some helium, and it was only after that point that light could travel freely through space. Before that moment, the universe was, in a sense, foggy, opaque. Light couldn't get anywhere. After that moment, the fog cleared, and light began its long journey outward. We can still detect the faint afterglow of that moment today. It's called the cosmic microwave background, and it surrounds us in every direction, a very faint whisper of heat left over from the earliest light the universe ever produced. From there, gravity slowly did its quiet work. Clouds of hydrogen and helium gas, ever so slightly denser in some places than others, began to pull inward on themselves. Over millions of years, these clouds collapsed and thickened, and in their cores, pressure and heat built up so much that something remarkable happened. Nuclear fusion ignited. Talk more and about the first that in a little while, about how stars are born and how they eventually die, and about what happens afterward. But for now, just picture it. Total darkness for hundreds of millions of years, nothing but drifting gas. And then, one by one, in scattered pockets across an unimaginably large canvas, lights beginning to switch on. That's where we're going to go next. But for now, just breathe. Let the size of it settle over you. Not as something overwhelming, but as something quiet. You are impossibly small in an impossibly large place. And that's all right. You don't have to hold any of it up. Let's talk about stars now. It holds it not just as pinpricks of light in the sky, but as things that are actually born, that actually live, and that actually die, sometimes in the most dramatic ways imaginable. A star begins its life inside something called a nebula, which is really just a big, cold cloud of gas and dust drifting through space. Some of these clouds are genuinely enormous, stretching across dozens or even hundreds of light years. Inside them, gravity is always quietly at work, and eventually, some part of the cloud becomes just a little denser than the rest. Once that happens, a kind of slow collapse begins. That denser clump pulls in more gas around it, and as it does, it also pulls in on itself, getting smaller and smaller, denser and denser, hotter and hotter. This can take hundreds of thousands of years, sometimes longer. A slow, patient contraction in the freezing dark with nothing to witness it happening. Eventually, the core of that collapsing clump becomes so hot and so dense that hydrogen atoms begin fusing together into helium. This is nuclear fusion, and it releases a tremendous amount of energy. That energy pushes outward, fighting against the inward pull of gravity, and when those two forces settle into balance, a star is born. It begins to shine. That balance between gravity pulling in and fusion pushing out is basically the entire story of a star's life. As long as that balance holds, the star simply sits there, burning steadily, sometimes for billions of years. Our own sun is a fairly average, middle-sized star, and it's been fusing hydrogen into helium for about 4.5 billion years already. It has, roughly, another 5 billion years of that fuel left before things start to change. Which means the sun is right around the middle of its life. Not young, not old. Comfortably, quietly, in the middle of things. But not every star gets a life like the sun's. What happens next depends almost entirely on how much mass a star has. Smaller stars, ones with less mass than our sun, actually live the longest. Some of the smallest stars, called red dwarfs, burn their fuel so slowly and so efficiently that they can shine for trillions of years. Trillions, which is strange to think about because the universe itself is only 13.8 billion years old. That means not a single red dwarf star has died of old age yet anywhere in the entire history of the universe. Every red dwarf that has ever formed is, in a sense, still a child, still burning through the earliest chapters of an extraordinarily long life. Medium-sized stars, like our sun, eventually run out of hydrogen fuel in their cores. When that happens, the core contracts and heats up even further, while the outer layers of the star swell up dramatically. The star becomes what's called a red giant, growing so large that in our sun's case, it will eventually swallow up Mercury, then Venus, and quite possibly reach all the way out to where Earth currently orbits. After that red giant phase, a star like our sun will gently puff its outer layers off into space, forming a beautiful, glowing shell of gas called a planetary nebula. All that will remain behind is the collapsed, super-dense core, called a white dwarf, about the size of Earth, but containing roughly the mass of the entire sun. A single teaspoon of white dwarf material would weigh several tons, if you could somehow bring it back to Earth and put it on a scale. The white dwarf will then simply cool, slowly, for trillions of years, fading from white to yellow to a dim, dark ember that may never fully go dark within the current age of the universe. Ones with far more mass than our sun live very different lives. They burn through their fuel much faster, sometimes in just a few million years instead of billions, because their enormous mass means enormous pressure and heat in their cores. They live fast, in cosmic terms, and they die in the most violent way a star can die. When a massive star runs out of fuel, it can no longer hold itself up against its own gravity. The core collapses in on itself in less than a second, an unimaginably fast implosion for something so large, and then rebounds outward in a catastrophic explosion called a supernova. For a brief period, a single supernova can outshine an entire galaxy of billions of stars combined. Just one dying star, briefly, brighter than everything else around it put together. What's left behind depends on how massive the original star was. Sometimes it leaves behind a neutron star, an object so dense that a teaspoon of it would weigh billions of tons. Neutron stars are so compact that if you took the mass of our entire sun and squeezed it down into a sphere about the size of a city, that's roughly what you'd end up with. And if the original star was massive enough, the core doesn't stop collapsing at all. It keeps collapsing, past the point of forming a neutron star, past any known limit, until it forms something so dense that nothing, not even light, can escape its gravity. A black hole. We'll spend more time on black holes shortly, because they deserve it. But for now, Just sit with this. Every heavy element in your body, the calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged inside the core of a star and scattered across space when that star died, sometimes gently, sometimes in a supernova of unimaginable literally violence, made of old starlight and old stardust. The atoms that make up you were once part of a star that lived and burned and eventually died, long before the Earth even existed. In a very real, very literal sense, you are a small, temporary, walking arrangement of very old cosmic material. And someday, in the very distant future, those same atoms will return to the universe, to be recycled again into something else entirely. There's no need to feel anything sad about that. If anything, it's rather beautiful. You're not separate from the universe, watching it from the outside. You are the universe. For a while, about black holes now, looking at itself, they tend to sound frightening at first, mostly because of the name. But once you understand what they actually are, they become less like monsters and more like one of the strangest, quietest phenomena the universe has ever produced. A black hole isn't a hole in the sense of an empty gap or a tunnel. It's the opposite of empty. It's an area where an enormous amount of mass has been squeezed into an incredibly small space. So small and so dense that its gravity becomes overwhelming. Gravity, as you may already know, is caused by mass bending the space around it. A black hole simply bends space so much, so severely, that nothing which enters can ever climb back out. Not a spaceship, not a beam of light, nothing. The boundary around a black hole, the point past which nothing can escape, is called the event horizon. It isn't a physical surface. There's no wall there, nothing solid to touch. It's simply the point of no return, an invisible line drawn in space itself. Most black holes form the way we just talked about, from the collapsed core of a massive star after it runs out of fuel and can no longer support its own weight. Those are called stellar black holes, and they tend to be a handful of times more massive than our sun, maybe up to a few dozen times, all squeezed down into a region smaller than a city. But there's another kind of black hole, far larger and far stranger, sitting at the centers of most galaxies, including our own. These are called supermassive black holes, and they can contain the mass of millions or even billions of our own galaxy. There is a supermassive black hole called Sagittarius A star. It contains about 4 million times the mass of our sun, all crushed into a region not much bigger than our solar system. And our entire galaxy, all 100 to 400 billion stars of it, slowly orbits around that black hole, the way planets orbit a sun, just on a vastly larger and slower scale. Our sun takes about 230 million years to complete one full orbit around the center of the galaxy. The last time our sun was in its current position, relative to the galactic center, dinosaurs hadn't even evolved yet. Here's something that tends to surprise people. If you were somehow able to safely orbit a black hole from a comfortable distance far outside the event horizon, it wouldn't actually pull you in any more strongly than a star of the same mass would. Gravity from a black hole isn't magically stronger than gravity from anything else of equal mass. It's simply concentrated into a much, much smaller space, which means you can get far closer to that mass than you ever could to a star. And the closer you get to any mass, the stronger its pull becomes. It's the closeness that makes black holes dangerous. Not some special things about black holes involves time itself. According to Einstein's theory of general relativity, gravity doesn't just bend space, it also bends time. And the stronger the gravity, the slower time passes, relative to someone farther away. Near a black hole, this effect becomes extreme. If you watched a friend falling toward a black hole from a safe distance, you would see them moving slower and slower as they approached the event horizon, their light stretching and dimming, until, from your perspective, they seem to freeze there, forever, never quite crossing the line. But from their own perspective, inside their own experience, they would cross that line completely normally, feeling nothing unusual at that exact moment, and continue on. Two completely different experiences of the exact same event, both equally true, depending entirely on where you happen to be standing. Scientists once thought we might never actually see a black hole directly, since by definition, no light escapes them, so there'd be nothing to see. But in 2019, an international team of astronomers using a network of telescopes around the entire planet, working together as one enormous virtual telescope the size of Earth itself, managed to capture the first ever image of a black hole's shadow, silhouetted against the glowing, superheated gas swirling around it. It looked like a fuzzy, glowing ring of orange light surrounding a dark circle, and it belonged to a supermassive black hole in a galaxy called M87. About 55 million aren't destructive forces roaming the galaxy hunting for things to swallow, either. That's mostly a misconception from movies. If our sun were somehow instantly replaced with a black hole of the exact same mass, which it never will be, the Earth would simply continue orbiting exactly as it does now. The gravity wouldn't change at all, because the mass wouldn't have changed at all. It would just get very dark and very cold rather quickly. Slightly less dramatic than being sucked in, but a good deal less exciting for a movie. There's also something almost poetic about black holes and endings. Some of the most massive stars in the universe, the ones that burned the brightest, the ones that lived the shortest, most intense lives, end their stories by becoming the densest, quietest, most patient objects in the universe. From explosive, roaring death to something that simply sits in the dark, silently bending space and time around itself for what may be trillions of years to come. It's worth remembering, as we drift further into this, that black holes are not empty. They're not absences. They are, in a way, the most concentrated presence anything can have. All that mass, all that gravity, all that history, folded down into almost nothing at all, and yet capable of shaping the movement of an entire galaxy around. Back to our own solar system, the small, familiar neighborhood we happen to live in. At the center of it all is the sun, which accounts for about 99.8% of all the mass in the entire solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, makes up less than 1/4%. If the solar system were a household budget, the sun would be almost the entire paycheck, and everything else would be the loose change left over. Let's drift outward from the sun, planet by planet, slowly. First comes Mercury, the smallest planet, and the closest to the sun. Mercury has almost no atmosphere to speak of, which means there's nothing to hold heat in or keep it out. During the day, temperatures can climb past 400 degrees Celsius, hot enough to melt lead. But at night, with no atmosphere to trap any of that warmth, temperatures can plunge to nearly -180 degrees Celsius. Mercury experiences some of the most extreme temperature swings of any object in the solar system, all because it has nothing wrapped around it to soften the difference between days. Similar in size to Earth, sometimes called Earth's twin, though it's really nothing like Earth at all once you look closer. Venus has a thick, crushing atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid drifting through its sky. This atmosphere traps heat so effectively that Venus is actually the hottest planet in the solar system, hotter even than Mercury, despite being farther from the sun. Surface temperatures on Venus average around 460 degrees Celsius, hot enough to melt certain metals. The pressure on the surface is roughly 90 times that of Earth, similar to being nearly a kilometer deep in Earth's oceans. And strangely, Venus rotates so slowly and in the opposite direction from most planets that a single day on Venus, one full rotation, actually takes longer than a full year on Venus. Then comes Earth, our home, the only place, as far as we currently know, anywhere in the entire universe where life exists. Earth sits in what scientists sometimes call the habitable zone, the comfortable range of distance from the sun where temperatures allow liquid water to exist on the surface. Not so close that oceans boil away, not so far that they freeze solid, just close enough, just far enough. A very narrow, very lucky window, and we happen to be sitting right the red planet, colored by iron oxide, essentially rust, covering much of its surface. Mars is home to the largest volcano in the entire solar system, Olympus Mons, which stands about 22 kilometers tall, roughly 2.5 times the height of Mount Everest. It also has a canyon system called Valles Marineris that stretches over 4,000 kilometers long enough to stretch across the entire continental United States. Mars once likely had rivers, lakes, and possibly oceans of liquid water billions of years ago, before it lost most of its atmosphere and became the cold, dry, dusty world it is today. Beyond Mars lies the asteroid belt, a wide ring of rocky debris left over from the early solar system, material that never quite managed to form into a proper planet, likely because of Jupiter's powerful gravity constantly disturbing it. Despite how it's often shown in movies, the asteroid belt is actually mostly empty space. If you were flying a spacecraft through it, The odds of accidentally colliding with an asteroid are extraordinarily low. There's simply an enormous amount of space between each rock. Then we reach Jupiter, the giant of the solar system. Jupiter is so massive that it contains more than twice the combined mass of every other planet in the solar system put together. Its most famous feature, the Great Red Spot, is a giant storm larger than the entire planet Earth that has been raging continuously for at least a few hundred years and possibly much longer. Jupiter also has an enormous family of moons, with over 90 confirmed so far, including Ganymede, which is actually larger than the planet Mercury. Famous for its stunning rings, made up of countless particles of ice and rock, ranging from tiny grains to chunks the size of houses, all orbiting the planet in a thin, flat disk. Saturn is so much less dense than the other planets that if you could somehow find a bathtub large enough, Saturn would actually float in water. Beyond Saturn lies Uranus, a pale blue-green planet that is tilted almost completely on its side, likely the result of an ancient collision. Because of this extreme tilt, each pole of Uranus experiences about 42 years of continuous sunlight, followed by 42 years of continuous darkness, an incredibly long, slow version of day and night compared to what we experience here on Earth. And finally, Neptune, the most distant of the official planets, a deep, vivid blue world with the fastest winds recorded anywhere in the solar system, reaching speeds of over 2,000 kilometers per hour. Neptune is so far from the Sun that it takes about 165 Earth years to complete a single orbit. It has only been observed to complete one full orbit since its discovery in 1846. And out beyond Neptune lies a distant, icy world called Pluto, which was considered the 9th planet for decades until it was reclassified in 2006 as a dwarf planet, a decision that remains, to this day, a topic some people still feel surprisingly strongly about. That's our solar system. 8 planets, one dwarf planet with a very devoted fan base, at least 200 known moons scattered among them, and one quiet, steady star at the center of it all, holding everything gently, not just our own, but some of the strange, beautiful, and unexpected moons scattered across the solar system. Our own moon is, in many ways, one of the strangest in the entire solar system, simply because of how large it is compared to Earth. Most moons are tiny compared to the planet they orbit, but our moon is about a quarter of the diameter of Earth itself, an unusually large ratio. The leading theory for how it formed is that about 4.5 billion years ago, a Mars-sized object collided with the young Earth, and the debris from that enormous collision eventually gathered together and formed the moon. In a very real sense, the moon may be made of pieces of Earth itself, and pieces of whatever that ancient object was, fused together and cooled into the pale, quiet companion that has circled us ever since. The moon is also slowly drifting away from us, at a rate of about 3.8 centimeters every year, roughly the speed your fingernails grow. It's a slow, gentle separation, so slow that it will take hundreds of millions of years to make any noticeable difference. But it is happening, quietly, right now, even as you lie there listening. The moon is also responsible for the ocean tides here on Earth, its gravity gently pulling on the water across the planet's surface as it orbits us. And interestingly, the moon is tidally locked with Earth, meaning it rotates at exactly the same rate that it orbits us, which is why we only ever see one side of it from Earth. The far side of the moon was a complete mystery until spacecraft finally photographed it in 1959. Now, let's drift out to Jupiter's moons for a moment, because a few of Jupiter's 4 largest moons is the most volcanically active body in the entire solar system. more active even than Earth. Its surface is constantly being reshaped by hundreds of active volcanoes, some spewing material hundreds of kilometers into space. This intense volcanic activity is caused by the powerful gravitational pull of Jupiter and its other moons, constantly flexing and stretching Io's interior, generating enormous heat through friction deep inside the moon. Europa, another of Jupiter's large moons, is covered in a thick shell of ice. But underneath that ice, scientists believe there is a vast, liquid ocean, kept warm by tidal heating similar to what powers Io's volcanoes. That hidden ocean may contain more liquid water than all of Earth's oceans combined. And it's one of the most promising places in our solar system to search for signs of microbial life, hidden away safely beneath the frozen surface. And then there's Titan, the largest moon of Saturn, and one of the most fascinating places in the entire solar system. Titan has a thick atmosphere, thicker than Earth's, and it's the only place in the solar system, other than Earth, known to have stable liquid on its surface. But it's not water. Titan is so cold, hundreds of degrees below freezing, that its lakes, rivers, and seas are made of liquid methane and ethane instead. Rain falls there too, methane rain, drifting slowly down through a hazy orange sky, filling rivers that carve through an alien, a smaller moon called Enceladus, covered entirely in bright, reflective ice. So reflective that it's actually one of the brightest objects in the entire solar system. Enceladus has geysers at its south pole, tall plumes of water vapor and ice particles that erupt continuously from cracks in its icy surface, spraying material out into space, some of which actually forms one of Saturn's fainter rings. Underneath that ice, like Europa, Enceladus is believed to hide a global ocean of liquid water, kept warm deep beneath its frozen shell. Even Neptune has an unusual moon, called Triton, which orbits in the opposite direction from Neptune's rotation, the only large moon in the solar system to do so. This backward orbit strongly suggests that Triton wasn't originally formed alongside Neptune at all, but was instead a wandering object, captured by Neptune's gravity long ago, likely from the distant, icy region beyond Neptune known as the Kuiper Belt. So many moons, so many quiet, strange little worlds, orbiting endlessly around their much larger companions. Some frozen and cracked, some erupting with volcanoes, some possibly hiding oceans, and maybe even life, deep beneath their icy shells, patiently waiting in the dark, unseen, unexplored. Let's zoom back out again, past the planets, past the moons, out into the wider galaxy we call home. Our galaxy, the Milky Way, is a barred spiral galaxy, which means it has a central bar-shaped region of stars, with long, curving spiral arms sweeping outward from it like a slowly turning pinwheel. Our entire solar system sits inside one of those spiral arms, called the Orion Arm, a relatively minor, unremarkable arm, roughly 2/3 of the way out from the galactic center toward the edge. The Milky Way is enormous, roughly 100,000 light-years across. That means light itself, again the fastest thing there is, would need 100,000 years just to cross from one side of our galaxy to the other. And our galaxy contains, again, somewhere between 100 billion and 400 billion stars, along with an enormous, invisible halo of something called dark matter, which we'll talk about a little later. If you've ever looked up on a very clear, dark night, far away from city lights, and seen a faint, hazy band of light stretching across the sky, that was the Milky Way itself. You were looking edge-on into the disk of our own galaxy, seeing the combined, blurred light of countless stars too distant and too faint to make out individually, all blending together into that soft, pale river of light across the sky. Galaxies themselves come in a few different shapes. Spiral galaxies, like our own, with their sweeping arms. Elliptical galaxies, which are more rounded, oval-shaped collections of stars, often older, with less new star formation happening inside them. And irregular galaxies, which don't have any particular defined shape at all, often the result of past collisions or gravitational disruptions from nearby. Our galaxy has actually merged with smaller galaxies before, and it will do so again. And in the distant future, the Milky Way is on a slow collision course with our nearest large galactic neighbor, a spiral galaxy called Andromeda, currently about 2.5 million light-years away. Andromeda and the Milky Way are drifting toward each other at roughly 110 kilometers per second, and current estimates suggest they will begin merging in about 4 to 5 billion years. Despite how dramatic that sounds, actual collisions between individual stars during this merger are expected to be extremely rare, because even within a galaxy, the space between stars is so vast that they're unlikely to actually strike one another. Instead, the two galaxies will slowly pass through and around each other over hundreds of millions of years, gravity gradually reshaping both of them, eventually merging into a single, larger galaxy, sometimes nicknamed Milkomeda, long after our sun has already reached the end of its life. Beyond our own galactic neighborhood lie galaxy clusters, groups of galaxies bound together by gravity, sometimes containing hundreds or even thousands of individual galaxies. Our own Milky Way belongs to a small cluster called the Local Group, along with Andromeda, a smaller spiral galaxy called Triangulum, and dozens of smaller dwarf galaxies scattered around them. And beyond that, galaxy clusters themselves are organized into even larger structures called superclusters, vast filaments, and walls of galaxies stretching across hundreds of millions of light years, separated by enormous, nearly empty voids. Our local group belongs to a supercluster called Laniakea, a Hawaiian word meaning immense heaven, which stretches across roughly 500 million light-years and contains around 100,000 galaxies. The universe starts to look less like scattered points of light and more like a vast, glowing web. Threads of galaxies stretching across unimaginable distances, with huge, quiet, empty voids in between. Some cosmologists have compared the large-scale structure of the universe to a neuron, or to the roots of a tree, or to foam. Whatever comparison you reach for, it's a structure built slowly, patiently, over billions of years, by nothing more than gravity quietly pulling matter together, one gentle tug at a time. And somewhere in one small arm of one ordinary galaxy, in one small, unremarkable corner of one supercluster among countless others, there's a small yellow star and a small blue planet orbiting it. And on that planet, right now, there's you, lying quietly in the dark, listening to all of this. Now let's talk about something strange. Something that scientists know is out there, can measure the effects of, and yet still cannot directly see or fully explain. Dark matter. Here's the problem that led scientists to dark matter in the first place. When astronomers study the way galaxies rotate, they run into something odd. Based on the visible matter in a galaxy, the stars, the gas, the dust, the galaxy shouldn't be able to hold itself together while spinning as fast as it does. The outer stars should simply fly off into space, the same way you'd go flying off a merry-go-round, spinning too fast if you weren't holding on tightly enough. And yet, galaxies don't fly apart. Something is holding them together, some extra source of gravity, far more than the visible matter alone can account for. That missing gravity is attributed to dark matter, a form of matter that doesn't emit light, doesn't reflect light, doesn't interact with light in any way we've been able to detect. It's invisible, in the most literal sense. We can't see it with any telescope, in any wavelength of light, ever built. But we can see its effects. Dark matter's gravity bends and distorts light from more distant galaxies passing near it, an effect called gravitational lensing. And scientists have used this effect to essentially map out where dark matter must be sitting, even though it remains completely invisible itself. Astonishingly, current estimates suggest that dark matter makes up about 27% of the entire universe. All the normal matter we know and understand, stars, planets, gas, dust, you, me, every living thing, every star ever observed, makes up only about 5% of the universe's total content. Dark matter alone outweighs it by more than 5 to 1. Honestly, nobody knows for certain yet. It doesn't seem to be made of the same particles that make up regular matter. Some scientists believe it might be made of an entirely undiscovered type of particle, one that interacts with regular matter only through gravity and essentially nothing else. Others have proposed different explanations entirely. It remains one of the biggest open questions in all of modern physics, an invisible scaffolding holding galaxies together, silently, everywhere, and we still don't fully know what it's made of. And then there's an even stranger mystery, called dark energy. In the late 1990s, astronomers studying distant supernovae made an unexpected discovery. The expansion of the universe, which we mentioned earlier, that stretching of space that began with the Big Bang, isn't slowing down over time the way most scientists had expected it to, due to the pull of gravity from all the matter in the universe. Instead, the expansion is speeding up. The universe isn't just growing, it's growing faster and faster as time goes on. Something is pushing space apart, some kind of energy embedded in space itself, and it appears to make up roughly 68% of the entire universe. Combined with dark matter's 27%, that leaves only about 5% of the universe as the kind of ordinary matter we can actually see, touch, and understand. In other words, everything you've ever seen, every star, every planet, every person who has ever lived, every book, every ocean, every mountain range, all of it together makes up only a small fraction of everything that exists. The vast majority of the universe is made of something we still don't fully understand, quietly shaping the fate of everything in ways we're only beginning to grasp. But also, strangely, a comforting one. There is still so much left to discover, so much mystery left in the universe, waiting patiently for someone, someday, to understand it a little better. You don't have to solve any of it tonight. You can simply let it be a mystery, resting quietly in the back of your mind, and drift off to sleep with it there. Let's shift for a while from the vast and ancient to something much more recent, something within human memory. Let's talk about the history of us actually reaching out into space ourselves. For nearly all of human history, space was something we could only look at, a ceiling of mystery above us, studied through myth, then later through mathematics and lenses, but always from a distance, always from the ground, always just out of reach. That changed remarkably quickly in the 20th century. The very first artificial object to reach space was a satellite called Sputnik 1, launched by the Soviet Union on October 4th, 1957. It was small, about the size of a beach ball, and it did nothing more than orbit the Earth, emitting a steady radio beep. But that simple beep, picked up by radios around the world, marked the beginning of the space age. Suddenly, humanity had placed something of its own making into orbit around its home planet. Just 4 years later, in April of 1961, a Soviet cosmonaut named Yuri Gagarin became the first human being to travel into space, orbiting the Earth once aboard a spacecraft called Vostok 1. The entire flight lasted just under 2 hours, and Gagarin became, almost instantly, one of the most famous people on the planet, the very first human to see Earth from outside of it. The United States, determined to catch up, sent astronaut Alan Shepard into space shortly afterward. And then, in February of 1962, John Glenn became the first American to orbit the Earth. This period became known as the space race, a period of intense competition between the United States and the Soviet Union, each nation striving to outdo the other, milestone by milestone. The most famous in the new frontier came on July 20th, 1969, when the American spacecraft Apollo 11 landed on the surface of the moon. Astronaut Neil Armstrong became the first human being to step onto another world, followed shortly after by fellow astronaut Buzz Aldrin, while a third astronaut, Michael Collins, orbited quietly above in the command module, waiting for their return. An estimated 600 million people around the world watched or listened to that moment happen live, an enormous portion of the entire population of Earth at the time, all watching together as a human being walked on another celestial body for the very first time in the history of our species. In total, 12 human beings have walked on the surface of the moon, all of them American astronauts, all of them during the Apollo program between 1969 and 1972. No human being has walked on the moon since December of 1972, though there are current plans, through NASA's Artemis program, to return astronauts to the lunar surface in the coming years, including, for the first time, a woman and a person of color among the crews. Space exploration didn't stop with the moon, though. Robotic spacecraft have since traveled to every planet in our solar system and beyond. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, took advantage of a rare alignment of the outer planets to fly past Jupiter, Saturn, Uranus, and Neptune, sending back our first close-up images of these distant worlds. Both Voyager spacecraft are still functioning today, decades later, and have since left our solar system entirely, becoming the first human-made objects to travel into interstellar space. Voyager 1, currently the most distant human-made object from Earth, is now more than 24 billion kilometers away, and its radio signals, traveling at the speed of light, currently take over 22 hours. Carry a golden record, a phonograph disc containing sounds and images meant to represent life and culture on Earth. Greetings in dozens of languages, music from around the world, and natural sounds like wind, rain, and thunder. It was included in case, someday, in the unimaginably distant future, some other form of intelligent life encounters the spacecraft drifting silently through the vast emptiness between the stars. Closer to home, the International Space Station has been continuously occupied by rotating crews of astronauts since November of 2000, orbiting Earth at an altitude of roughly 400 kilometers, traveling so fast that it circles the entire planet once every 90 minutes. Astronauts aboard the station witness a sunrise or sunset roughly every 45 minutes, meaning they experience about 16 sunrises and sunsets every single day. And more recently, robotic rovers have continued exploring the surface of Mars, sending back extraordinary images and data. The Perseverance rover, which landed on Mars in February of 2021, is currently searching for signs of ancient microbial life, and even carried a small helicopter named Ingenuity, which became the first aircraft to achieve powered flight on another planet. All of this, every single mission, every rocket launch, every photograph sent back from the edge of our solar system, happened within the lifetime of people who are alive today. In the grand, patient timescale of the universe we've been talking about tonight, in the billions of years since the Big Bang, humanity has only just begun looking outward for the smallest, most recent sliver of time. And already, we've placed footprints on another world, sent machines to the edges of our solar system, and launched a golden record out into the endless dark, quietly hoping that someone someday other planets might find. Not the ones in our own solar system, but planets orbiting other stars entirely, out among that vast scattering of lights we talked about earlier. These are called exoplanets, short for extrasolar planets. And for most of human history, we had absolutely no way of knowing whether they even existed. Stars are so bright, and planets are so comparatively small and dim, that spotting a planet orbiting a distant star seemed, for a long time, essentially impossible. The very first confirmed exoplanet orbiting a sun-like star was discovered in 1995, orbiting a star called 51 Pegasi, roughly 50 light-years away. It was a huge moment in astronomy, proof that planets really did exist beyond our own solar system, something long suspected but never actually confirmed until that point. Since then, the pace of discovery has been extraordinary. As of recent counts, astronomers have confirmed more than 5,000 exoplanets, with thousands more candidates awaiting confirmation. And this is very likely just the smallest possible fraction of what's actually out there. Based on current data, scientists estimate that most stars in our galaxy host at least one planet, which means there could be hundreds of billions of planets in the Milky Way alone, most of which we haven't even detected yet, let alone studied closely. Astronomers find these distant planets using a few clever methods. One of the most common is called the transit method, where astronomers watch a star's brightness very, very closely, waiting for a tiny, regular dip in that brightness, caused by a planet passing directly in front of the star from our point of view, blocking a small fraction of its light. These dips are incredibly subtle, sometimes less than a fraction of a percent of the star's total brightness. Yet, with sensitive enough instruments called the radial velocity method, looks for a very slight wobble in a star's position caused by the gravitational pull of an orbiting planet tugging on it ever so slightly. Even though a planet is far smaller than its star, its gravity still pulls back on the star just a little, causing it to wobble in a small, regular pattern that can be detected in the star's light. Some of the exoplanets discovered are wildly different from anything in our own solar system. There are hot Jupiters, gas giants orbiting so close to their stars that they complete an entire orbit in just a few days, with surface temperatures hot enough to vaporize metal. There are super-Earths, rocky planets larger than our own but smaller than gas giants. There are planets orbiting two stars at once, similar to the fictional planet Tatooine, with actual double sunsets. And there are rogue planets, drifting alone through interstellar space, not orbiting any star at all, having been flung out of their original solar systems long ago, wandering endlessly through the dark, cold silence between the stars. Of course, the biggest question hanging over all of this is whether any of these planets might harbor life. Scientists focus heavily on the habitable zone, that same comfortable range of distance from a star where temperatures allow liquid water to exist, which we mentioned earlier when discussing Earth. Several exoplanets discovered so far do sit within their star's habitable zone, and some are relatively close to Earth's size, which makes them especially exciting candidates for further study. One particularly interesting system is called TRAPPIST-1, a small, cool star about 40 light-years away, orbited by 7 roughly Earth-sized planets, 3 of which sit within the star's habitable zone. It's one of the most promising systems we currently know of for the potential existence of liquid water, and possibly, though this remains entirely unconfirmed, like the James Webb Space Telescope, launched in December of 2021, have begun analyzing the atmospheres of some of these distant exoplanets directly, searching for chemical signatures that might indicate the presence of water or even biological activity. It's an extraordinarily difficult task, studying the faint chemical fingerprint of a planet's atmosphere from dozens of light-years away. But it's now, for the first time in human history, actually possible. We haven't found definitive proof of life beyond Earth yet, not on any exoplanet, not on Mars, not in the hidden oceans of Europa or Enceladus. But we also haven't found any proof that we're alone either. The search continues, quietly, patiently, one distant star at a time, one tiny dip in brightness at a time, one faint atmospheric signature at a time. And there's something comforting, oddly, in simply not knowing yet. The universe still holds its biggest questions close, unanswered, waiting. There's still discovery left to be made, still mystery left in the sky above you. Right now, as you lie there listening, slowly drifting further from wakefulness, while somewhere out there, quietly, patiently, that search continues without you, and will still be continuing tomorrow and the day after that. Let's slow down even whether more, you're awake, and talk about some of the smaller wanderers of our solar system. The comets, the asteroids, the little pieces of rock and ice that drift quietly through space, occasionally passing close enough for us to notice them. Comets are often described as dirty snowballs, a mix of ice, dust, and rocky material left over from the very early formation of the solar system, over 4.5 billion years ago. Most comets spend the vast majority of their existence in the outer regions of the solar system, far beyond Neptune, in two distant regions called the Kuiper Belt and the Oort cloud. The Oort cloud, in particular, is thought to be a vast, spherical shell of icy objects surrounding the entire solar system, starting somewhere beyond the orbit of Neptune and possibly extending nearly halfway to the next nearest star. It's so far away, and its objects so small and dim, that we've never actually directly observed the Oort cloud itself. Its existence is inferred mostly from the behavior of long-period comets, the ones that seem to come from that far outer distance. Occasionally, the gravity of a passing star or some other gentle gravitational nudge sends one of these icy objects tumbling inward toward the sun. As a comet approaches the inner solar system and warms up, the ice on its surface begins to vaporize, releasing gas and dust that forms a glowing cloud around its core, called the coma, along with the long, glowing tail that comets are famous for. That tail always points away from the sun, regardless of which direction the comet itself is traveling, because it's shaped by the solar wind and radiation pressure constantly pushing. Periodic comets follow predictable, repeating orbits and return to the inner solar system at regular intervals. The most famous of these is Halley's Comet, which returns to the inner solar system roughly every 76 years. It was last visible from Earth in 1986, and it's expected to return again in 2061. Many people alive today will get the rare chance to see it twice in their lifetime. Decades apart, a strange, quiet thread connecting different chapters of a single human life to the same ancient, icy visitor. Asteroids, unlike comets, are made mostly of rock and metal, without much ice. Most asteroids in our solar system orbit within the asteroid belt, that wide region between Mars and Jupiter we mentioned earlier. They range enormously in size, from tiny pebbles to Ceres, the largest object in the asteroid belt, which is actually large enough to be classified as a dwarf planet in its own right, nearly 1,000 kilometers across. Every so often, a small asteroid or piece of comet debris enters Earth's atmosphere, burning up due to friction with the air, creating a brief, glowing streak of light across the sky. We call these meteors, or more casually, shooting stars, even though they have nothing to do with actual stars at all. Most meteors we see are caused by objects no larger than a grain of sand or a small pebble, completely burning up harmlessly, high in the atmosphere, tens of kilometers above the ground. Meteor showers happen when Earth passes through a trail of debris left behind by a comet as it orbited the Sun on a previous pass through the inner solar system. As Earth moves through this trail of scattered dust and small particles, many of them burn up in our atmosphere around the same time, causing a noticeable increase in meteors visible in the sky, sometimes dozens per hour, all appearing to radiate outward from roughly the same happen at the same time every year, since Earth's orbit crosses the same debris trails annually. The Perseid meteor shower, for example, occurs every August, caused by debris left behind by a comet called Swift-Tuttle, and is one of the most reliable, most watched meteor showers of the year, often producing 60 or more visible meteors per hour under dark, clear skies. Occasionally, a larger object, big enough to survive the trip through the atmosphere without completely burning up, will actually reach the ground. Once it lands, whatever remains is called a meteorite. Most meteorites found on Earth are quite small, but every so often, a genuinely large object has struck the planet, sometimes with dramatic consequences. The most famous example happened about 66 million years ago, when an asteroid roughly 10 to 15 kilometers wide struck what is now the Yucatan Peninsula in Mexico, creating an impact so powerful it triggered a mass extinction event, believed to be responsible for wiping out the dinosaurs, along with roughly 75% of all species on Earth at the time. Modern astronomers now actively track thousands of near-Earth objects, asteroids and comets, whose orbits bring them relatively close to our planet, carefully calculating their paths decades into the future to make sure nothing large is quietly heading our way unnoticed. So far, nothing currently tracked poses any significant threat, and space agencies continue refining ways to detect and potentially deflect any future object that might. It's a strange thought, in a way, that the sky above you isn't entirely empty and calm. It's full of quiet wanderers, icy comets slowly looping through the outer darkness on thousand-year orbits, ancient rocky asteroids drifting silently in that wide belt beyond Mars, and tiny grains of dust burning up harmlessly overhead nearly every single night, whether anyone happens to be looking up to see them on the star closest to us, the one we rarely think of as a star at all, simply because it's so familiar, so present, so woven into every single day of our lives. The Sun. The Sun formed about 4.5 billion years ago, from the same collapsing cloud of gas and dust that eventually formed the rest of our solar system. It contains about 99.8% of all the mass in the solar system, as we mentioned earlier, and it is, by an enormous margin, the largest object anywhere near us. You could fit about 1 million Earths inside the volume of the Sun. At its core, the Sun is fusing hydrogen into helium at a temperature of around 15 million degrees Celsius, releasing an almost incomprehensible amount of energy in the process. Every single second, the Sun converts about 600 million tons of hydrogen into helium. Some of that mass, a tiny fraction of it, gets converted directly into pure energy, following Einstein's famous equation relating mass and energy. That energy takes an extraordinarily long time to make its way from the Sun's core out to its surface, sometimes estimated at anywhere from tens of thousands to over 100,000 years, as it slowly bounces and scatters its way outward through the incredibly dense material inside the Sun, before finally escaping as light. Which means, in a strange way, the sunlight warming your skin on any given day may have begun its journey inside the Sun's core tens of thousands of years ago, long before recorded history began, slowly making its way to the surface, before finally leaving the Sun and crossing the 93 million miles to Earth. The Sun, called the photosphere, has a temperature of around 5,500 degrees Celsius. And yet, strangely, the Sun's outer atmosphere, called the corona, which extends millions of kilometers out into space, is far hotter than the surface itself, sometimes reaching over 1,000,000 degrees Celsius. Exactly why the corona is so much hotter than the surface below it remains one of the more puzzling open questions in solar physics. The Sun isn't a perfectly calm, unchanging ball of light either. Its surface is constantly shifting and churning, marked by sunspots, darker, slightly cooler regions caused by intense magnetic activity, and solar flares, sudden, powerful bursts of energy and radiation. Sometimes, The sun releases enormous eruptions of charged particles called coronal mass ejections, sending billions of tons of material out into space. When these eruptions happen to be aimed toward Earth, they can interact with our planet's magnetic field, creating beautiful auroras, the northern and southern lights, dancing curtains of green, pink, and purple light in the skies near the polar regions. Strong enough eruptions can also, on rare occasions, disrupt satellites, power grids, and radio communications here on Earth. The sun also follows an approximately 11-year cycle of activity, gradually rising and falling between periods of relative calm and periods of intense sunspot and flare activity, driven by the slow, complex reversal of its magnetic field, which flips entirely, north becoming south and south becoming north, roughly every 11 years as well. The sun is about halfway through its expected lifespan. In roughly 5 billion years, once it exhausts the hydrogen fuel in its core, it will begin the transformation into a red giant, swelling enormously, likely engulfing Mercury and Venus, and quite possibly reaching all the way out to Earth's current orbit. Long before that happens, though, hundreds of millions of years from now, the sun will have already grown gradually brighter and hotter, eventually making conditions on Earth's surface too extreme to support life as we currently know it. A process that will unfold so slowly, so gradually, over such an immense span of time, that it will pose no immediate concern to us or to countless generations to come. Eventually, after its red giant phase, the sun will gently shed its outer layers into space, forming a glowing planetary nebula, leaving behind a small, dense white dwarf, roughly the size of Earth, that will simply cool quietly, slowly, for trillions of years afterward. But that's an unimaginably long time from now. Tonight, the sun is simply doing what it's done every single day of your entire life and every day of every life that has ever existed on this planet, quietly burning 93 million miles away, holding the entire solar system gently in its orbit, waiting patiently just below the horizon, ready to rise again in a few hours. Whether you're awake to see it, something we touched on earlier, because it's worth sitting with for longer. The strange relationship between space and time, and the way looking outward into the universe is also, always, a way of looking backward into the past. Light travels incredibly fast, about 300,000 kilometers every single second. Fast enough to circle the entire Earth about 7.5 times in the time it takes you to blink. And yet, even at that staggering speed, the universe is so large that light still takes a very, very long time to cross it. We measure these vast distances in light years, the distance light travels in a single year, which works out to about 9.5 trillion kilometers. It's a unit of distance, not time, even though it has the word year built into it, which can be a little confusing at first. When we say a star is 10 light years away, we mean the light we're currently seeing left that star 10 years ago and has been traveling toward us silently ever since. This means that whenever you look up at the night sky, you're never truly looking at the universe as it exists right now. You're looking at an enormous collection of different moments in the past, all layered on top of each other. The moon you're seeing as it was about 1.25 seconds ago, the sun as it was about 8 minutes ago, the nearest stars as they were several years ago, more distant stars in our own galaxy as they were centuries or even thousands of years ago. And some of the more distant galaxies visible through powerful telescopes we're seeing as they existed billions of years ago, long before Earth itself had even formed. In a very real sense, the night sky is a kind of time machine, though not one you can climb inside. It's more like layers of an old photograph album, spread out across the sky, each point of light showing you a different, older moment, frozen at the instant that particular light left its source. If some other form of intelligent life on a planet 50 light-years away pointed a sufficiently powerful telescope toward Earth tonight, they wouldn't see you lying there, listening to this. They would see Earth as it was 50 years in the past, whatever was happening on our planet at that time, light having only just now completed its 50-year journey to reach them. The most extreme version of this idea involves the very edge of what we can observe. There's a boundary called the observable universe, the farthest distance from which light has had enough time to reach us since the universe began, roughly 13.8 billion years ago. Beyond that boundary, there may be more universe, quite possibly a great deal more. But its light simply hasn't had time to reach us yet, and may never reach us at all, especially with the universe's expansion continuously stretching that distance even farther. Some of the most distant galaxies we've observed, using extremely powerful telescopes like the James Webb Space Telescope, show light that left its source only a few 100 million years after the Big Bang itself. Looking at those distant ancient galaxies means looking almost all the way back to the very beginning of everything, catching a glimpse of the universe in its earliest, youngest form, before most of the stars and galaxies we know today had even begun to form. There's something quietly humbling about all of this. Every plan you've ever made, every worry you've ever carried, every single day of your life has taken place in what amounts to an infinitesimally small sliver of time compared to the age of the universe around you. And yet, in that small sliver, here you are, capable of looking up, capable of understanding, even just a little, the light arriving from countless different moments scattered across billions of years of cosmic history. You don't need to hold on to any of it tightly. The stars will still be there tomorrow night, and the night after that, continuing to send their old, patient light toward Earth, long after you've fallen asleep, long after tonight is over, long after this particular video has ended. The light was already on its way before you were born, and it will keep arriving long after, whether you happen to be there to see it or not. Let's slow down even further now and talk about something a little different. Not the physics of the universe, but the way human beings, for thousands of years, have looked up at that same scattering of stars and quietly told stories about it. Constellations are, in a way, one of humanity's oldest shared projects. Long before telescopes, long before we understood what stars actually were, people all over the world looked up at the same night sky and noticed patterns. Groupings of bright stars that, if you squinted and used your imagination, seemed to form shapes. A hunter, a bear, a pair of twins, a great winged bird. It's worth remembering that the stars in a constellation usually have no real relationship to each other at all. They're not actually grouped together in space. A constellation is simply an illusion of perspective, stars that happen to appear close together from our particular vantage point here on Earth, even though, in reality, they might be dozens or even hundreds of light years apart from one another. Some much closer to us, some much farther. all just happening to line up along the same direction in our sky. Take Orion, one of the most recognizable constellations in the night sky, easily spotted by the three bright stars in a neat, straight row that form Orion's belt. The stars that make up Orion appear to belong together, but they range enormously in actual distance from Earth. Betelgeuse, the reddish star marking Orion's shoulder, is about 640 light-years away, while Rigel, marking his foot, is roughly 860 light-years away. They only appear close together because of the angle we happen to be viewing them from. Throughout human history, looked at the same scattering of stars and told entirely different stories about them. The ancient Greeks saw Orion as a great hunter placed in the sky by Zeus. In ancient Egypt, that same group of stars was associated with Osiris, the god of the afterlife and rebirth. In parts of Aboriginal Australian astronomy, entirely different patterns and stories were drawn from the night sky altogether, sometimes using the dark spaces between the stars, rather than the stars themselves, to form shapes like a great emu stretched across the sky, outlined by dark clouds of dust within the Milky Way rather than by bright points of light. The star patterns themselves haven't changed much throughout recorded human history, at least not enough to notice with the naked eye over a single lifetime. But they do change, very slowly, over extremely long periods of time, as stars drift along their own individual paths through the galaxy. Tens of thousands of years from now, many familiar constellations will have gradually shifted into unfamiliar new shapes, the same stars slowly rearranging themselves as they continue their long, patient orbits around the galactic center. Sailors, for thousands of years, relied on the fixed, predictable patterns of the night sky for navigation, long before satellites, long before GPS. The North Star, Polaris, sits almost perfectly aligned with Earth's axis, meaning it appears to stay nearly motionless in the sky throughout the night, while every other star appears to slowly rotate around it. Sailors could look toward Polaris and instantly know which direction was north, a simple, elegant piece of natural navigation. Many written star names we still use today have been passed down from ancient Arabic astronomy, preserved and refined over centuries. Names like Betelgeuse, Aldebaran, and Vega all come from Arabic roots, carried forward through centuries of careful astronomical scholarship, long before modern telescopes existed, based purely on careful, patient observation of the sky, with nothing but the naked eye. There's something quietly comforting in realizing that whatever you're looking at in the night sky tonight, assuming you happen to catch a glimpse of it before falling asleep, people have been looking up at roughly that same view for tens of thousands of years. Different cultures, different languages, different stories, different beliefs, all looking at the same quiet scattering of ancient light, all finding their own patterns, their own meaning, their own comfort in it. You don't have to know a single constellation by name to feel that same quiet connection. It's simply there, waiting, every clear night, the same as it's always been, for as long as human beings have had the good sense to lie back. Look up. Let's talk about a few more strange objects scattered throughout the universe. Things that, when they were first discovered, genuinely puzzled the scientists who found them. We talked earlier about neutron stars, the incredibly dense, collapsed cores left behind after a massive star explodes as a supernova. Some neutron stars have an especially strange property. They spin extremely fast. Some rotate several hundred times every single second, faster than a kitchen blender, despite containing more mass than our entire sun. As they spin, some neutron stars emit powerful beams of radiation from their magnetic poles. And because the magnetic poles usually aren't perfectly aligned with the star's spin axis, those beams sweep around through space, the same way a lighthouse beam sweeps around as it rotates. If one of those beams happens to sweep past Earth during its rotation, we detect a brief, extremely regular pulse of radiation, over and over, with incredible precision. We call these objects pulsars, and they were first discovered in 1967 by a graduate student named Jocelyn Bell Burnell, who noticed an oddly regular, rhythmic radio signal coming from a fixed point in the sky. The signal was so perfectly regular that, for a brief period, some scientists jokingly wondered whether they might have accidentally discovered a signal from an alien civilization. They nicknamed the source LGM-1, short for Little Green Men, before quickly determining that the true explanation, a rapidly spinning neutron star, was every bit as remarkable, even without aliens involved. Some pulsars are so precise in their timing that astronomers use them as extraordinarily accurate cosmic clocks, rivaling the precision of some of the best atomic clocks ever built here on Earth, all powered by nothing more than the steady, mechanical spin of a collapsed stellar core. Tens of thousands of light years, which are, in a very real sense, some of the brightest, most energetic objects in the entire known universe. At the heart of many distant galaxies sits a supermassive black hole, similar to the one at the center of our own Milky Way. In some galaxies, especially younger, more distant ones, that supermassive black hole is actively pulling in an enormous amount of surrounding gas and dust. As that material spirals inward, it heats up dramatically due to friction and gravitational forces, forming a swirling, glowing disk around the black hole called an accretion disk. In the most extreme cases, this process releases such an enormous amount of energy that the resulting object, a quasar, can outshine the combined light of every single star in its entire host galaxy, sometimes by a factor of hundreds or even thousands, all powered by material falling into a single black hole at the galaxy's center. Quasars are so extraordinarily bright that we can detect them from billions of light years away, making them some of the most distant individual objects that astronomers are able to study in any real detail. Looking at a distant quasar means looking back billions of years into the past, catching a glimpse of galaxies as they existed in the much younger, more chaotic universe, long before galaxies like our own had settled into their current, comparatively calm and quiet state. There are also strange, brief, incredibly powerful bursts of energy called gamma-ray bursts, among the most energetic, explosive events known to occur anywhere in the universe. A single gamma-ray burst, lasting anywhere from a fraction of a second to several minutes, can release more energy in that short window than our own sun will release over its entire 10 billion year lifetime. These are thought to be caused by the collapse of extremely massive, rapidly spinning stars into black holes, or by the violent collision of two neutron stars merging, an even more recently discovered mystery. Extremely brief, powerful pulses of radio waves, lasting only milliseconds, arriving from distant galaxies for reasons that still aren't entirely understood. Some are known to repeat, occasionally, from the same source, while others have only ever been detected once. Astronomers are still working to understand exactly what causes them. It's worth remembering, as you drift further into sleep tonight, that the universe is not a calm, silent, unchanging place. Even though it can certainly feel that way when we look up at a peaceful night sky, it's full of extraordinarily violent, extraordinarily energetic events, unfolding constantly, in galaxies far beyond our own, entirely unnoticed by us most of the time, except for the faint, patient light and radio waves that eventually make their long journey across the universe. And quietly arrive Rasios, here, to be noticed, studied, and wondered about. Let's talk, gently, about one of the biggest open questions of all. Are we alone in the universe? Given everything we've talked about tonight, the sheer scale of the universe, the hundreds of billions of stars in our galaxy alone, the 2 trillion or so other galaxies out there, and the fact that most stars appear to host at least one planet, it seems almost statistically unlikely that Earth would be the only place, anywhere, that ever developed life. And yet, so far, we haven't found any confirmed evidence of life anywhere else. No signals, no structures, no definitive biological signatures in the atmosphere of any exoplanet. Nothing yet, despite decades of searching. This tension between how likely life seems given the scale of the universe and how empty and silent the universe has appeared so far is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who is said to have once simply asked, during a casual lunch conversation with colleagues in 1950, "Where is everybody?" There are many possible explanations, and nobody knows for certain which one, if any, is correct. One possibility is that life itself is common, but intelligent. Technology using life is exceptionally rare. Simple microbial life might be relatively easy for the universe to produce, given enough time and the right conditions. But the specific evolutionary path that leads to complex, intelligent life, capable of building telescopes and radio transmitters, might be extraordinarily unlikely. A rare, fragile fluke that took billions of years and a long chain of specific circumstances to occur even once. Another possibility is that intelligent civilizations are relatively common, but they simply don't last very long, at least not in a way that overlaps with our own narrow window of searching. Perhaps advanced civilizations tend to face significant challenges, whether environmental, technological, or otherwise, that limit how long they survive after developing the ability to communicate across space. If a civilization only broadcasts detectable signals for a few hundred years out of a universe that's been around for over 13 billion years, the odds of 2 such civilizations happening to overlap in time, while also being close enough to detect each other, become remarkably small. There's also the simple issue of distance and time, the very thing we spent so much time discussing earlier tonight. Even if intelligent civilizations exist elsewhere in the galaxy right now, The distances involved are so enormous that meaningful communication becomes incredibly difficult. If a civilization exists 1,000 light years away and sent us a message today, we wouldn't receive it for another 1,000 years. And any response we sent back would take another 1,000 years to reach them. A conversation stretched out over thousands of years, with each side possibly having changed dramatically or ceased to exist entirely long before the other's message. We simply haven't searched long enough or thoroughly enough yet. Organized efforts to search for extraterrestrial intelligence, sometimes called SETI, have been underway since the 1960s, primarily listening for artificial radio signals from distant stars. But we've only been capable of transmitting or detecting radio signals for around a century ourselves, an extraordinarily brief moment compared to the age of the universe. It's entirely possible other civilizations exist or have existed, but their window of detectable activity simply never lined up with our own brief window of listening. There's also a newer, quieter approach, searching not for deliberate signals, but for indirect evidence, searching the atmospheres of distant exoplanets for gases that shouldn't naturally occur together without some biological process producing them, searching for unusual patterns of light that might indicate large-scale structures built by an advanced civilization. So far, nothing definitive has turned up, but the search continues, growing more sensitive, more sophisticated, with every passing year. Whatever the answer eventually turns out to be, there's something quietly profound in simply not knowing yet. If we are alone, entirely alone, in this vast, ancient, impossibly large universe, then life itself and everything that came from it, art, music, curiosity, love, the simple act of lying quietly in the dark and wondering about the stars becomes almost unbearably precious and rare. And if we're not alone, if somewhere out there, right now, some other form of life is looking up at their own sky, wondering the exact same question about us, then we're part of something even larger and stranger than we currently understand. A universe quietly, patiently, capable of producing minds like ours. The question remains open, and there's no need to resolve it tonight. You can simply let it rest there, gently, unanswered, and let yourself drift off into sleep instead, beneath a sky that may or may not be watching you back. Let's take one last long, slow look outward, this time toward the future. Not next year, not next century, but the almost incomprehensibly distant future of the universe itself. We already talked about some of the nearer-term events. In about 5 billion years, our sun will swell into a red giant and eventually collapse into a quiet white dwarf. In about 4 to 5 billion years, our galaxy, the Milky Way, will begin merging with the Andromeda galaxy, the two slowly combining into a single, larger galaxy over hundreds of millions of years. But let's go further still. Over the next trillion years or so, star formation across the universe will gradually slow down and eventually stop almost entirely. Right now, the universe still has plenty of hydrogen gas available, drifting through galaxies waiting to collapse into new stars. But that supply isn't infinite. Slowly, gradually, galaxies will use up their available gas, and fewer new stars will be born. The stars that already exist will continue living out their lives, some ending in dramatic supernovae, some quietly fading into white dwarfs, but fewer and fewer new ones will take their place. Very slowly, over trillions of years, the universe will grow dimmer. Not suddenly, not dramatically, but gradually, one star at a time, one galaxy at a time, as star formation tapers off toward nothing. Eventually, on a timescale of many trillions of years, essentially every star that will ever form will have already formed, lived, and died. The remaining objects, white dwarfs, neutron stars, and black holes, will continue drifting through their galaxies, cooling, fading, without any new light being generated to replace what's lost. Some theories suggest that even matter itself may not be permanent. Certain theoretical models predict that protons, the building blocks of atoms, might eventually decay. Though this process, if it happens at all, would take place over a timescale so long, possibly beyond 10 to the power of 34 years, that it makes even the current age of the universe look like a single passing second by comparison. Black holes, too, are not expected to last forever, despite how permanent and immovable they seem. According to theoretical work by physicist Stephen Hawking, black holes very slowly emit a faint form of radiation, now called Hawking radiation, and over unimaginably long periods of time, they gradually lose mass and eventually evaporate away entirely. For a supermassive black hole, this process could take on the order of 10 to the power of 100 years, a number so large it has its own name, a googol, far, far longer than the current age of the universe. Eventually, in this far future scenario, sometimes called heat death, the universe may reach a state of maximum entropy, an extremely low energy, extremely spread out, extremely cold state, where no more usable energy remains to power stars, or light, or any organized activity of any kind. Just a vast, dark, nearly empty expanse, spread out across distances too large to properly imagine, drifting quietly onward, essentially forever. It's worth saying clearly, this is an unimaginably distant future. We're talking about timescales so long that comparing them to the current age of the universe, 13.8 billion years, is a little like comparing the age of the universe to a single blink of an eye. None of this is something to worry about, tonight or any night, for the rest of human history. It's simply one possible current best understanding of where all of this, eventually, very slowly, peaceful in that too, if you let it be. The universe isn't in a hurry. It never has been. It took billions of years just to form the first galaxies. It will take trillions more before the last stars quietly fade out. Time, on this scale, stops feeling like something to race against and starts feeling like something enormous and patient, something you're simply allowed to rest inside of for the small, quiet moment that happens to be your life. You don't have to think about any of this again after tonight. Go away, wife, gently. And you can simply let it settle, and let it mind, into the back of your settle, Thailand. Driv de tuk der unfettered, and hunteletly dot narza presently had every unimal in the autumn of Garzen. Hewful peep, but gently, drimmest something tones delivering out a try into nine. I am simply wrapping out all your mind it's again after movement. How to commons flayed sounds battleground enormousness, or expent from uval, this tonight. Do you fresting from that all you go? I will have to thinkly let it settle, gently to the nightlier settled, gently into the back of your mind, the way a stone settles slowly to the bottom of still water, and let yourself drift, unhurried. Last section before we close out for the night. Let's slow down even further. No big themes, no long explanations, just a gentle collection of smaller facts about space, one after another, softly, like counting stars instead of sheep. A day on Venus is longer than a year on Venus. It rotates so slowly that it completes less than one full spin before it finishes an entire orbit around the Sun. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on planet Earth combined. Neutron stars can spin so fast that their surface moves at a meaningful fraction of the speed of light, some rotating hundreds of times every single second. The footprints left behind by Apollo astronauts on the Moon are expected to remain visible for millions of years, since the Moon has no wind, no rain, and no atmosphere at all to erode them away. The largest known star discovered so far, a red hypergiant called UY Scuti, is so enormous that if you placed it where our Sun currently sits, its outer surface would extend out past the orbit of Jupiter. It snows on Mars, though the snow is made partly of frozen carbon dioxide, sometimes called dry ice, rather than only frozen water. Saturn isn't the only planet with rings. Jupiter, Uranus, and Neptune all have faint ring systems too. They're just far less prominent and far harder to see than Saturn's. If two pieces of the same type of metal touch each other in the vacuum of space, they can sometimes permanently bond together, a phenomenon called cold welding. Because there's no air or oxide layer between them to prevent it, the way there normally would be here on Earth. One day on Earth is very slowly getting longer, by about 1.5 milliseconds every century, as the Moon's gravity gradually slows. The canyon in the solar system, Valles Marineris on Mars, is so vast that it would stretch from California to New York if you placed it here on Earth. Space is not entirely silent, in the sense that sound waves have been detected traveling through the extremely thin gas surrounding some galaxy clusters, though the notes are far too low, by many octaves, for human ears to ever actually hear them directly. A single day on Mercury, one full rotation, takes about 59 Earth days. But because of its unusual orbit, a single solar day there, from sunrise to sunrise, actually takes about 176 Earth days. There is a planet discovered in 2011, orbiting a star about 4,000 light-years away, that scientists believe may be almost entirely made of crystallized carbon, essentially an enormous diamond, several times the size of Earth. The gap between Saturn's rings and the planet itself is large enough that you could comfortably fit all 7 other planets in the solar system inside it, stacked side by side. Light from the sun that eventually reaches your eyes tonight, if it's a clear night, has already spent tens of thousands of years slowly working its way out from the sun's core, before finally crossing the 93 million miles to Earth in just about 8 minutes. Uranus was almost named after King George III of England by the astronomer who discovered it, before the international astronomical community eventually settled on the name we use today instead. There's a nebula, called the Boomerang Nebula, about 5,000 light-years away, that is the coldest known natural place in the entire universe, colder even than the leftover background radiation from the Big Bang itself, at around 1 degree above Jupiter, has been shrinking gradually over the past century, and scientists aren't entirely certain whether it will eventually disappear completely or stabilize at some smaller size. Astronauts aboard the International Space Station grow slightly taller during their time in space, sometimes by a few centimeters, because the lack of gravity allows their spine to gently stretch and decompress before slowly returning to its normal length after they return to Earth. And finally, tonight, wherever you happen to be lying right now, you are moving. Not just spinning with the Earth's rotation, and not just orbiting the Sun. Our entire solar system is also orbiting the center of the Milky Way at roughly 230 kilometers every single second. And our galaxy itself is moving through the universe relative to the cosmic microwave background at roughly 600 kilometers per second. Even lying perfectly still, even fast asleep, you are, right now, hurtling through space at a genuinely staggering speed, and you'll never feel. Let's talk about one particular photograph. Just one image out of everything we've discussed tonight that manages to hold a great deal of this entire conversation inside a single frame. In 1990, the Voyager 1 spacecraft, the same one we mentioned earlier, the most distant human-made object from Earth, was leaving the solar system, having already completed its main mission of studying the outer planets. Vele, ultimately shaved the Isreswestri, having already completed its mission of studying the outer planets. At the request of astronomer Carl Sagan, mission engineers turned Voyager 1's camera around, back toward the inner solar system, from a distance of about 6 billion kilometers away, and took a photograph of Earth. In that photograph, Earth appears as a single, pale blue point of light, less than a pixel across, suspended in a beam of scattered sunlight, surrounded by the vast darkness of space. Our entire planet, every mountain, every ocean, every city, every person who has ever lived, reduced to a barely visible speck, caught almost by accident in a stray beam of light, in a photograph taken from 6 billion kilometers away. Carl Sagan later wrote about that image, describing Earth as a mote of dust, suspended in a sunbeam, and reflecting on just how small, how fragile, and how singularly precious that pale blue dot really is. Every human joy and suffering, every war, every celebration, every quiet, private moment of someone's individual life, all of it has unfolded entirely on that single, it's a strange kind of perspective to sit with. On one hand, deeply humbling. In a universe of 2 trillion galaxies, hundreds of billions of stars in our own galaxy alone, we are, physically, almost unimaginably small and insignificant. And yet, on the other hand, there's something quietly remarkable in the fact that, on that one small, pale blue dot, something happened that, as far as we currently know, hasn't happened, or at least hasn't been detected, happening anywhere else in the entire universe. Matter arranged itself into something that could think and wonder and look outward and build spacecraft and turn a camera around from 6 billion kilometers away just to take one small photograph of home. You are, in this exact moment, lying somewhere on that same tiny pale blue dot. Every person you've ever loved, every place you've ever been, every mountain you've ever seen, and every ocean you've ever swum in, exists on that same small point of light, drifting quietly through the same vast darkness we've spent all this time talking about tonight. There's no need to feel small in a way that feels heavy or discouraging. It can simply feel quiet instead, peaceful. Whatever you're carrying with you tonight, whatever thoughts followed you into bed, Whatever worries or plans or half-finished to-do lists are still lingering somewhere in the back of your mind, all of it, every single bit of it, is happening on that same small, pale, impossibly lucky dot of light, suspended gently in the dark, quietly turning, quietly orbiting, quietly continuing on, the same as it always has. You can let it all rest there now, gently, for tonight. It will still be there tomorrow, exactly where you left it. For now, there's nothing else you need to do, and nowhere else you need to be, except right here, right now, drifting slowly towards sleep, on this small, pale, blue, endless idea before we close out for the night. One that tends to help a lot of people finally feel the true scale of everything we've talked about tonight, in a way that numbers alone sometimes can't quite manage. It's called the cosmic calendar, an idea popularized by Carl Sagan, and it works like this. Imagine taking the entire 13.8 billion year history of the universe, from the Big Bang all the way to this exact moment, right now, and compressing all of it down into a single calendar year. January 1st, the very first moment, is the Big Bang. And midnight on December 31st is right now, tonight, this exact second. On this scale, every single day represents about 37 million real years. Every single hour represents about 1.6 million years. And every single second represents about 438 years. Let's walk through it slowly. The Big Bang happens in the first instant of January 1st. For a long stretch after that, nothing especially eventful happens, at least not on the scale of forming stars and galaxies as we know them. The Milky Way galaxy itself doesn't begin forming until sometime in March. Our own sun, and the rest of our solar system, doesn't form until around September 1st, roughly 2/3 of the way through the entire cosmic year. Earth forms shortly afterward, around September the 9th. The very first simple life on Earth, simple single-celled organisms, appears remarkably early after that, around the end of September, but for an enormous stretch of time after that, for months and months on this calendar, life remains simple, single-celled, and largely unremarkable, just quietly persisting, generation after generation. Multicellular life doesn't really begin to flourish until sometime in mid-December. The first fish appear around December 19th. The first land plants and insects around December 20th. Dinosaurs don't appear until December 24th. And they're wiped out in that mass extinction event we discussed earlier, on the evening of December 30th. Still more than a full day remaining in the entire cosmic year. Mammals, having existed quietly in the background for a while already, begin to flourish and diversify after that extinction throughout the day of December 31st, the very last day of the entire cosmic calendar. And human beings, modern humans, the kind capable of language, art, and eventually astronomy, don't appear until the last few minutes of December 31st, somewhere around 11:52 p.m., on the very last night of this entire 13.8 billion year calendar. All of recorded human history, every ancient civilization, every empire, every war, every book ever written, fits into the final 10 seconds before midnight. The moment the first human being walked on the moon happens in the final fraction of the final second. And this exact moment, right now, you, lying there, listening to this, drifting slowly toward sleep, is happening in the very last, immeasurably small sliver of that final second. Right at the very edge of midnight, on December 31st, at the end of a calendar that represents the entire staggering history of the universe. It's a strange thing to sit with. Every single thing you've ever known, every person, every place, every memory, fits into a space so small on this scale that it barely registers at all. And yet, here you are anyway, a genuinely tiny, genuinely brief flicker of existence, still somehow capable of understanding the scale of the calendar you're standing in that smallness. If anything, there's a kind of quiet permission in it. You don't have to carry the weight of 13 billion years on your shoulders tonight. You only have to carry tonight. This one, small, quiet moment, right at the edge of midnight, drifting gently towards sleep, while the rest of the universe continues on, unhurried, exactly as it always has, and exactly as it always will. Long after this particular second, that's where we'll leave things for tonight. We've traveled a long way together in this short amount of time, at least in terms of distance. From the size of the observable universe down to the surface of Mars, from the birth of the very first stars to the quiet, eventual fading of the very last ones, from black holes bending time itself to a single pale blue photograph of home, taken from 6 billion kilometers away. None of it needs to be remembered. None of it needs to be studied, or written down, or carried forward into tomorrow. It was simply something gentle to rest your mind on for a while. A soft, slow wandering through the universe, meant to carry you quietly towards sleep. If your eyes are still open right now, that's all right. You can simply let them close whenever they're ready. There's nothing left to do. Nothing left to figure out. Nothing left to hold on to. The stars will still be there tomorrow night, exactly where you left them, patiently continuing on, exactly as they have for billions of years, whether you're watching or not. Thank you for spending this time with me and with Astronomical Essence. Sleep well, rest easy, and I'll see you again, gently, next time. Good night.